My name's Andy Truby from Truby Stevenson, and I'd like to welcome you to this evening's live broadcast, webinar on the subject of the key updates to the second generation of Eurocode 2. This is an FIB UK event with assistance from the Institution of Structural Engineers. Just take you through a couple of slides relating to FIB. For those who don't know the organisation, FIB is the International Federation for Structural Concrete. It's a not-for-profit organisation with lots of input from around the world. As you can see there, 104 countries, many corporate members and individual members. And effectively, the mission of FIB is everything to do with concrete, from research, scientific matters, practical matters, right through construction, design, and it's really to advance all of that knowledge on concrete and to share that knowledge with practitioners. There's the way that FIB is organised into a number of what they call commissions. I won't go through them all, but you can see here there's commissions, 10 commissions dealing with various different aspects of concrete design. And there's just a couple of images there of the current president, the deputy president who will become the president in a short time, and the previous president. There is also a young members group, and there's a link there which you'll get after the event. But and that obviously that's for the younger members of the organisation. The way that it's organised in the UK and in other national countries is there's an FIB UK, which is a group of companies which come together under the auspices of FIB, and our objectives are like the main objectives, really to spread knowledge and good practice. And this seminar is one of those knowledge sharing events. Our website is hosted by the Institution of Structural Engineers, and there's a link on the screen there. And maybe you can't read it, but in the box there's a list of the current membership. Membership involves consultants, contractors, universities and researchers, and manufacturers. So it's a very broad sort of group right across the whole discipline of everything to do with concrete. I forgot to mention client organisations in there too. The way that FIB produces its information is through lots of bulletins, which are technical guidance, really. These are the ones that were produced last year. Actually, number 97 there was produced December of 2020. And it's roughly about 4 or 5 bulletins a year. You can see the topics there. I won't go through them all. But we're over 100 now. One of the benefits of being a member or a part of the UK membership is that you get access to all of these publications and lots of details and information. There's also FIB produces the model code, and on the left there you can see that the latest model code is 2010. That sounds like a long time ago, and actually it is, and it certainly work's underway now to produce the next model code. Tony might touch on this in one of our speakers. The model code very much feeds in to Eurocode. So really the FIB model codes are usually ahead of where the Eurocodes are, and giving the sort of most recent thinking. In the middle there's a journal that's produced by FIB called Structural Concrete, which contains research papers. And on the right is an image of all of the publications produced in 2021, 6 volumes, each of 39 papers each. So lots of information in there. Anyway, that was really just to give you a bit of a headline as to what FIB is all about, but really down to the main events. We've got 2 speakers this evening to give us an insight into the updates to the Eurocode. They're going to sort of double team this. Firstly, I'll introduce Tony Jones. Tony's a principal structural engineer with the Concrete Centre. Tony has over 30 years experience in the design, research, investigation of concrete structures. And Tony currently has a key role as the UK head of delegation to the SEN committee, which deals with all of the Eurocodes. And the SEN committee is overseeing the development of the new code. And Tony, in his sort of day job, provides structural design guidance to the UK concrete industry. Tony will be ably supported by Craig Giaccio. Craig is a senior technical director with Arcadis, over 25 years experience, encompassing research and design, assessment and so on of rehabilitation of existing structures. And Craig is also on a technical group for SEN Committee on Structural Concrete. So enough from me. I'll join you again later for questions, but I'll now hand over to Tony. Tony.
Thanks, Andy. Okay, so what I'm going to focus on are generally the improvements to the current rules that are already in the Eurocode that you all know. Craig will talk a bit later about some of the new areas that will be covered in the next generation Eurocode. I'll look at the organisation of how we carry out the work, what the programme for the work is at the moment. I'll look at the key areas for improvement, and then new topics I'm going to hand over to Craig. So the organisation of SC2, which is the European committee that looks after both the maintenance and the development of new codes for concrete, is, as I show on this slide. I won't dwell on this too long, but what you see is that down the left-hand side, we have lots of working groups which contain experts. And as Andy said, sometimes those experts and those groups indeed very closely mirror groups in the FIB. So a lot of crossover with information from FIB coming into the development of new Eurocodes. In the middle, we have the main committee, which is SC2, which is the one I sit on. And then on the right-hand side, we had 3 project teams. And whereas on the left-hand side, these committees are sort of just groupings of experts, the project teams actually had contracts to produce various parts of the new generation of Eurocode. So project team 1, and that was what I'll largely be talking about their work now, which was updating the current code. Project team 2 was looking after the fire part, and I should say right from the start that the fire part and the part for the normal ambient design are basically in sync, moving through this process together. And then the third project team was led by Craig, who will speak to you in a minute, and that was looking at the additional items which we proposed right at the beginning of the process to include within the Eurocode. This is an overall view of the Eurocode process. So just to, again, emphasize, it's not just Eurocode 2 that is being updated, but all the Eurocodes are being updated. The preparation for this updated started 10 years ago with getting a mandate and getting that agreed within SEN to actually do the work. The actual technical work started in 2015. What we see is that probably the most important dates are the ones at the end, and that is by 2027, each national body, so in our case BSI, will have needed to have published the second generation Eurocodes for all parts, and then they get withdrawn in 2028. You see the phases in the interim phases, the technical phases that are there. We were lucky in that I think all of our work fell within phase 1 and phase 2, which is why the concrete Eurocode is a little bit ahead of some of the others. If we look at the program for Eurocode 2 itself, this is a snapshot of my spreadsheet, so I can keep track of things. You can see that last year, in terms of SEN activity, the main thing was what's known as an inquiry, and that's where a draft is sent out to all the countries to review, and then they vote to say whether they think that inquiry is fit to go to the next stage. Now, in the UK, that meant we spent the back end of last year doing a lot of calibration work and a lot of commenting, and we put in, as the UK, about 700 comments on part 1 of EN 1992. The total number of comments was from all national bodies was over 4,000. So now in SEN, we're in the process of comment resolution, trying to agree with all the different national comments, some of which clearly contradict each other, etc., reach a compromise to resolve them. At which point in August, if we carry on to programme, we will approve the next document to go to what's known as the formal vote. And this is basically last chance saloon. So actually during formal vote, there shouldn't be any further technical comments. Everything should be just editorial. So the formal vote process goes from the end of this summer through until April. The reason for taking so long is the first thing that has to happen is the document has to be translated into the official languages of the EU before it can then go out to be voted on formally. Obviously in the UK, we'll have some more calibration and commenting to do on that formal vote copy. And if we could carry on with the SEN activities, there'll be a 4 or 5 month period to review any final comments that come in with the formal vote. And assuming that formal vote is positive, the aim is to make the new text of the Eurocode available at the end of 2023. That won't be necessarily available generally, that'll be available to BSI, and then it becomes BSI's responsibility to determine when they actually publish that, albeit within that 2027 deadline. This program under UK here is sort of my best guess at the quickest that we could do it. And you see that probably sometime early in 2024, it's quite possible for us to publish the new second generation Eurocode 2 with its national annex. There will obviously need to be guidance documents, both formal BSI guidance through the PD documents and other informal supporting material in the terms kind of design guides that we often produce in the concrete centre, but also software companies need to update their software, etc., etc. So that will be an ongoing process which will continue well into 2025 probably. So that's the program at the moment. As I say, that is dependent on BSI, and they may decide that they don't want to publish Eurocode 2 without some of the other parts of the Eurocode being available, and that's all still to be agreed. So at a high level, it's quite clear from SEN that the objections, the aim was to reduce the number of NDPs and to enhance ease of use, and they gave these sort of 4 principles of enhancing ease of use. If you look, then translate that into the objectives for the project teams to Eurocode 2, we again wanted to reduce the number of NDPs, enhance ease of use. Durability was a big issue. You'll probably be aware that in the current Eurocode, in the UK, we effectively ignore what's in the Eurocode and refer through the national annex straight to BS 8500. And I think a number of other countries have a similar approach to not really paying much attention to it. Obviously, design by nonlinear finite element methods is much more common, and we wanted to set up some principles in there. It was felt that the size effect wasn't dealt with consistently, and that was one of the objectives, to sort that out. Early age thermomechanical design is just another word for early thermal cracking, Syria C60, Syria 766 type models. One of the other things that we wanted to do was integrate Eurocode Part 2, which is the bridges part, and Part 3 into Part 1, simply because we didn't really see why there was a need for different rules for different types of structure. And actually, when we looked at it, there was very little in the bridge code that was actually specific to bridges, and a lot of it was equally applicable to other either large structures or structures in exposed environments. So one thing we did right at the start of the revision process is we had what's known as a systematic review, and that's where we go out to the various members of SEN and ask them for their comments. And I just include this slide because it does give you quite a clear indication of where the areas were that the countries struggled with. And you can see if you combine shear and punching shear, they're by far the biggest area. Then there's cracking and anchorage and laps, and sort of those 4 areas between them dominate the specific comments. So throughout the drafting process, we I think there's been a disagreement, should we say, struggle to get consistency about what ease of use is. Is ease of use simple equations that have limited application and therefore can't be extended to other materials? Or is it physically more correct models which are sort of mechanically somewhat transparent, I wouldn't say completely transparent, but then can be applied to different situations? So when we talk about introducing new materials, you know, is the model flexible enough to actually be used with those new materials? I don't think there's really a single answer to this, but it's certainly something that's been testing us throughout the drafting process and through you know, the comments that come back. So one example of this is the change in the concrete design strength. We used to have an alpha CC term. The alpha CC term hid many sort of different effects in one fudge factor, if you like. And that's been changed. So now we have the ETCC factor, which is effectively a brittleness factor. So it reflects the fact that as concretes get stronger, the brittleness increases, and that has certain effects on design. And then we have the KTC factor, which is related to the effect of high sustained load. So theoretically, if you load a cube up to say 90% of its capacity and you leave it there for long enough, it will eventually fail under 90% of its capacity. And that needs to be taken into account. The corresponding effect that offsets this is if your cube is 2 years old, then it's probably 10% stronger at least than it was at 28 days. So there's sort of combined effects in this KTC factor. Anyway, what does it do? Well, if you recall, we have alpha CC as 0.85 in the UK, and the recommended value, which I think France and a few other, and Italy, for example, use, is 1. You can see that for the UK, if we go with this new ETA CC value and we stick to the recommended values, we'll actually end up with a slightly higher design compressive strength, right up until a strength of about 70 MPa. So for the UK, it's not a problem. For some of the other nations that use alpha CC as 1, they're not very happy with this. But there are other changes as well. Because we take into account brittleness in the ETA CC factor, the strain limitations for higher strength concretes have been removed. And in addition, although we've got confinement in the current code, there's no guidance on how you can use links to provide that confinement, and rules have been given. So I think it's going to be more normal to take into account confinement from links to calculate your column capacities. Actually, part of the reason the rules changed is because they reassessed a lot of column tests, taking into account the confinement from the links, and demonstrated the effect that's been seen. What this means is if you look at actual capacities, if you take the solid red line, and I'm sorry the graphic isn't particularly good, the solid red line is the line for alpha CC equals 0.85, and the dotted line is alpha CC equals 1. And then the lines going from yellow to blue are different levels of confinement. What you see is actually, if you take into account confinement explicitly, most of the results sit somewhere between 0.85, alpha is 0.85 and alpha is 1. So that gives us some confidence, I think, that there's a logic to these changes. So the next issue is shear. And as I said, shear was one of the areas that had a lot of comments in the initial phase. Now, the current simple variable truss method can still be used. In fact, the strut angle currently is limited between 1 and 2 point, cot theta of 1 and 2.5. It can now go down to cot theta equals 3, where you have pre-stress. So that's quite a helpful addition. But a more basic approach, detailed approach, basic in that it takes basic parameters into account, is also given. And in this case, you calculate the level of longitudinal strain on the neutral axis directly. And from that, you can get further efficiencies in your shear design. It's for those that have look at the Canadian method, it's not too far different from the modified compression field theory. So again, what we've tried to do is keep a simple method, but give a more advanced method where that people can use, where that will benefit them. Punch and shear. There was a lot of problems with punch and shear, the current rules. If you do design of footings correctly, it's actually an iterative procedure. The location of control perimeter at 2D doesn't really reflect where failure occurs. I think that's always been known, and the 2D was just a very convenient way of making the punch and shear capacity the same as the linear shear capacity. Unfortunately, we lose that with the new method. So there's this funny issue about what you do between the punch and shear check and a linear shear check. Again, size effects. It's known that slab slenderness affects the performance. So if you have a slab of the same thickness, the punch and shear capacity is more effectively on a shorter span. So thicker, shorter spans tend to give higher values. Efficiency of reinforcement. In the current code, it only really considers the effect of links and then making a model that's adaptable for new materials. So the basic model considers the formation of a circumferential shear crack. Now, we know that when you look at a slab and it's loaded, you quite often see radial cracks around a column if you look hard enough. But failure doesn't really start to become a concern until you start seeing some circumferential cracks. And we get a major dominating crack, and that's called the critical shear crack. So at a critical shear crack, you get a rotational deformation and potentially a shear deformation, as shown on the left-hand side there. And that derives so a shear resistance. And if you look at that shear resistance along the crack, obviously where the crack is smaller, you're going to transfer more shear than where the crack is wider. So your shear capacity is effectively related to this rotation. So if you then look at the rotation relationship, so our blue line could be a failure criterion, and then you load up one slab and it's a stiff slab, it will have a much higher shear capacity when it hits that failure criterion. So the top red line there, as it shows, is the case where shear occurs while the flexural reinforcement is still in the elastic regime. The middle one is probably the more usual case where you'll be getting some yielding locally of the reinforcement, but not general yielding. And then the lower one, where you get the lowest shear capacity, you've got full yielding of your flexural reinforcement. The control perimeter has changed. I already mentioned this. The 2D perimeter was considered not to be a very good approximation. And instead we have a perimeter. We still have the face shear, the perimeter at the face of the support, but we have another perimeter at 0.5 dV being the effective shear depth from the face of the column. You can also see that they formalized requirements for limitations at the end of walls, and indeed in this case for very big columns. This has been given in the UK in guidance before, but it's now and that guidance, in fact, was based on the FIB model code, is now implicitly included in the Eurocode. So let's start off with slabs with no links. We have an equation here based on this new perimeter. And you can see, in fact, that this dV over 2 perimeter isn't meant to reflect the edge of the shear crack. It's just an average, if you like, for the shear crack. We have a concrete term. We have a reinforcement term. We have a size effect. DDG relates to the size of the aggregate. So the size effect is a function of the aggregate size as well as the depth of the element. And then we have a concrete crushing check. So actually, the basic form of this equation is very, very similar to the current code. It's just the factors have changed somewhat. What we do have is this KPB factor. It's a shear gradient enhancement coefficient. Now, this I've seen various various physical descriptions of this, but I consider it as something that reflects the variation of shear stress around a column. And if you have a smaller column, then you can tolerate a larger variation percentage-wise of shear stress. So as well as that enhancement that takes into account this shear gradient, you can also refine your calculation by looking at the location of the point of contraflexure, because this affects the rotation, and by taking that into account, you can often increase your capacity. We have an axial prestress force as the current code. The benefit doesn't seem to be very large with the current proposals, so this is an area that's a slight concern. And then finally, you can get a benefit from membrane action. Now, the view of the experts was in fact that the traditional UK approach to punching shear implicitly relied on membrane action, and that was why we tended to have somewhat higher shears than the recommended values to the current code. The membrane action is written as an NDP, and actually the default position is you only use it when you're assessing an existing structure. But I think in the UK we'll probably try to use that in design to get closer to what our current design practice is. If we put shear reinforcement in, you can see now that we have a failure criteria for the concrete, and then a failure criteria including the links. And what you will see is that you have a rotation at which your concrete would have failed, but as the shear increases, your concrete contribution drops further, and your steel contribution increases up to a point when you're fully utilizing the steel. This is, I'm not even going to attempt to go through this rather complicated equation, but it's this equation that takes into account the loss, the drop in the concrete shear capacity, tau RDC, and then how much of the shear reinforcement capacity that you can derive from your rho WFY WD. Now, the two important the contribution of concrete can simply be calculated from the ratio of the design shear to the shear that the concrete could have carried on its own. And then the contribution of the reinforcement, you can see, relates to the size effect and the size of the reinforcement, etc., etc. So it's quite detailed assessment of the capacity of the reinforcement. Possibly more controversial is that we have a tau RD max, which we've always had in the UK. We have 2 tau RDC effectively as our current limit using the current rules. ETA-sys has been quite controversial, and I think it's clear that the values proposed in the current draft aren't acceptable to UK and Spain. Because it has this ETA-sys value does depend on the type of shear reinforcement, so it will encourage the use of shear studs, which is reasonable because they do have better anchorage than a normal single leg shear link that we tend to use for punching. So there are some benefits, but I think there's still some calibration to be done to get the right answers. At the outer perimeter, it's a similar calculation to the first perimeter. Obviously, the effective depth is reduced for a number of reasons. Firstly, because it assumes that the strut is picked up on the bottom steel. Now, this is theoretically interesting, but it's not current practice, and it seems to lead to quite conservative answers. So again, this is something the UK is challenging. And the concrete capacity also assumes that all the rotation occurs at this outer perimeter, which is again conservative and something that is currently being challenged. So I've already mentioned that the maximum shear reinforcement can be increased with the use of headed studs, and also potentially there's a greater effective depth allowed at the outer perimeter if you use studs. Although I think this will be an NDP, and I'm not sure there'll be any difference in the UK with that second point. So, you know, it would be wrong to say everything's done and dusted. We're in this process where we're trying to resolve the inquiry comments. What we can say is the issues relate to the maximum shear resistance at the first perimeter, i.e. your VRD max, the effective depth at the outer perimeter. There's some discrepancies in the rules with large columns and walls, which I think we've resolved now, and generally the economy of the design to try and get something aligned with what we get at the moment. And as I said earlier, I think NDPs will likely be introduced to resolve at least some of those issues. So some of the concerns about anchorage were the ease of use, and they wanted it, easy for standard cases. So that's one extreme. We want it easier, and then the other extreme, of course, is that actually we always assume an average bond stress along a bar, and that's not correct. It's very convenient, but it's actually not correct. So to try and address this, we've ended up with a table, which those who can remember BS 8110 will actually probably think that looks fairly familiar, and is certainly ease of use if you comply with the requirements in the note at the bottom. And the anchorage lengths are not too dissimilar to what we use presently. Then there's a refined model which the table's based on, and so if you don't comply with the table, or if you have some other benefits you want to take into account, we have this equation, the calibration factor. That's actually going to be an NDP, so countries can decide the level of reliability that they think they need for their anchorage lengths. We have a bond factor, again we have that at the moment. There's a factor on the stress, and what this does is it gives you a ratio of anchorage length to stress, but once you start using higher grade reinforcement, so the new standard will allow you to use reinforcement up to grade 700 compared to what we tend to use in the UK of 500, but that will then start penalising you in this anchorage length term. We also have a cover term, and that cover term can now be enhanced to allow for confinement. And that again can be quite beneficial, particularly where you've got links. Headed bars, there's a set of rules that say you can assume that your headed bar is anchored subject to the points that I've put there. If you can't comply with those requirements, there is a much more detailed an assessment method, which then directly takes into account the cover, etc., to the headed bar and the size of the headed bar, etc., etc. How useful this will be in the UK, I'm not sure. I would have thought in most cases we'd probably just try and comply with the requirements on the previous slide and assume your bar's anchored. I guess there may be issues where edge distances are reduced. So that this equation effectively is checking two things. It's checking the concrete crushing, and it's checking the side blowout of your headed bar. So if you stress the headed bar, you can blow the side off the element if you're not careful. There is also a rule that allows you to combine both the head and the typical bar anchorage. For obvious reasons, you can't use that for shear or confinement, because there you really are relying on anchorage at the end. So durability was another issue that was raised as an area to look at. The proposal is we have these exposure resistance classes. So across the top, you have your exposure classes, which are the same as currently and as given in A500. And down the left-hand side, you have a concrete which has an exposure resistance class. And this has some physical meaning in terms of testing this class, although there's still some arguments as to what test is the appropriate test and how it works in terms of responsibilities. But at least initially, I see it very, it should be very simple to relate the concretes that we currently have in BS 8500 to one of these exposure resistance classes. So you may find that a future version of 8500, rather than being set up as it is, giving covers for certain concretes, it will just say this concrete can be considered to be an RXE 4, for example. So I think this is a positive thing, because it not only does it give us the opportunity to be more consistent with the Eurocode approach, but it also means that as new concretes come through, concretes using different binders, perhaps lower carbon concretes, then they can be incorporated into design without too much effort. The last point there is just a point that, to get this to work properly as it's meant to work, we need EN 206, we need BS 8500, and we need Eurocode 2, and of course the UK national annex to Eurocode 2, all to align. I think that we'll need quite a bit of national guidance during that transition period as we get all our ducks lined up, so to speak. Cracking, again, another top area. There is a detailed approach, and it looks similar to the current code. It has some additional factors in there, and what we're finding is it tends to lead to larger crack widths in flexure, but smaller crack widths for tension. So predominantly, we see axial tension in the element when we're looking at restraint. So it seems to have quite a few efficiencies in terms of designing for restraint cracking, but actually seems to be less economic when we're considering flexure. Again, this is something where we're looking at how we can give nations a choice as to how they implement it. We have simplified methods as well. Again, these have proved very controversial, and I think these will probably be moved to an informative annex. What an informative annex means is that we can say in the national annex, either yes, use the annex as it is, or no, don't use the annex, or actually use this information instead of the annex. There's also a new annex on restraint cracking. At first glance, it looks very similar to Syria C660 or C766, its successor, but actually it's not the same. And I think we'll need again to look at how that affects those guidance documents and how we can get the best out of both. So in summary, the publication is second generation will be the culmination, as I said, of over 10 years of technical work. There was obviously administrative work going on long before that. The point that's been made throughout the process is that we're revising a code to be fit for 2040. So it needs to have the flexibility to incorporate developments as they come along. There's been a thorough assessment of current comments on the current Eurocode, and we've addressed them where we can. There are new theories in key areas, and I'm sure that will take some getting used to, and support from places like the Concrete Centre to try and show how you get through these new rules. And it's meant to deliver ease of use. I think only time will tell whether it's actually been successful with that. So I'm now going to hand over to Craig. As I said right at the beginning, Craig led the project team that was looking at predominantly the annexes, which have introduced a set of new materials into the second generation Eurocode 2. So hand over to you, Craig.
Thank you, Tony. Yes. So primarily, yes, as I was mentioning there, we within the work of the project team, we were looking at implementing new, not just materials, but provisions that weren't previously in 1992 part 1. So new materials wise, we've covered steel fiber reinforced concrete, strengthening of concrete structures with fiber reinforced polymer, effectively became carbon fiber reinforced polymer, reinforcement of structures, new structures with FRP reinforcement, and stainless steel was incorporated as well in way of, I'll explain a bit later. We did also, as part of the work of the project team, cover an assessment annex, which was looking at other provisions that were helpful for those assessing existing structures. I'll start with steel fiber reinforced concrete. I won't say too much of the material because I know it has been around for a little while, but we're talking obviously about concrete reinforced with fibers that might be up to sort of 60 millimeters long, very small in diameter, say 0.5 millimeter to 1 meter, but with very high strengths up to potentially 2 gigapascals. So provisions for incorporating this have been included in what's an informative annex. Tony outlined that a bit earlier in terms of what that is. So it's a set of new provisions that we as UK can choose to either implement or not. And based on where we are at the moment, there's a likelihood that the UK will implement those as well as an informative annex and just follow what they are. The aim of the work was to implement supporting clauses that enable the use of steel fibers in concrete, predominantly just increasing the tension strength, which I'll come to in a second. It was only steel fibers. There was discussion through the course of through the life of the project team around other fibers, specifically polypropylene fibers. There hadn't been a remit by SEN to look at that. There had been a request during the process by a group in Ireland actually to include, but I think the horse had effectively bolted and the stable door had closed, and that wasn't able to be done within the timescales. There are specific issues with them around ductility, particularly, and there are a lot of novel uses of steel fibers in concrete at the moment, particularly there are structures going up in Norway and in a couple of Eastern European countries where they're getting fairly adventurous with using them without much or any conventional reinforcement in some cases. So there was a lot of work done within the code about limiting how that was used. And obviously how the issue of ductility was dealt with within that. It was actually the first time that a codified approach had been implemented in, obviously, the UK or within Europe as well. So it was a bit of a journey to go down. Obviously, the main benefit from steel fibers is if you're comparing to plain concrete, you get a markedly increased tension strength. And the point of the provisions is to basically use that favorably in terms of capacity, and I'll show shortly what that actually means in terms of the strength gains. There is the possibility that once post cracking you get a little bit of softening, and then obviously the fibers take up, and you get the strength gain from the steel fiber reinforced concrete, and post cracking, you get either a hardening or a softening effect, which is covered in the standard up until a point at which you end your sort of residual strength. In terms of alignment of standards, which Tony has sort of alluded to previously, there are EN 206 actually partly covers this, and there are further developments ongoing within Technical Committee 104 to develop this as well. There are already European standards covering the production and testing of steel fibers, which made the codification relatively straightforward. So in terms of provisions that were implemented, there were obviously, I've already shown previously, the new stress-strain relationships for steel fiber reinforced concrete in tension. The provisions themselves don't change the compressive strength or the constitutive models for concrete in compression. It is solely for the tension, although some work has been done showing that there is some benefit with steel fibers in compression. There are obviously ductility provisions that I've set out. Probably the main issue is that I've alluded to earlier was around ductility. Now, the fibers themselves are very good in terms of gaining the strength gain post-cracking, and they do result in enabling fairly wide cracks, but there is quite a significant drop-off as crack widths open. And if relied on solely in terms of tension strength, there is a real issue in terms of ductility of structures. So a lot of thought and consideration was given to limiting the usage of provisions within the standard for fiber-only structures. And there are quite specific limits around how what type of structures you can use really with steel-only fibers. But there is a revised minimum requirement for a minimum reinforcement requirement, taking account the favourable effect of steel fibres being in the admixture of concrete. The provisions are effectively adjusted. Tony's already touched on the intent to have provisions in the main code that permit the use of newer materials such as steel fibres, and that has been done to a reasonable extent in the standard as it currently sits at the moment. They're not permitted for consideration in the standard as it is for fatigue. There isn't just enough information available to include provisions on that. In terms of what it does, you can see here the sort of what are called residual strength classes, which is the sort of post-cracking strength that you get. So FR3K, which is the strength that you consider in design, basically, for ULS calculations. You're getting up to strengths potentially of 10.4 megapascals for certain what are called ductility classes, obviously relating to fiber dosages, which is compared to characteristic values which can be used for the maximum strength concrete now in the standard of 100 or 115, C100, 115 of 3.6 megapascals. So some pretty considerable gains in strength there. They are going to be provisions which need to be used, I guess, by designers with some knowledge. There is links to specific parameters of effectively what's a crack width, a crack mouth opening design, to obtain these values of residual strength classes FR1K, which is your sort of post-cracking strength with a higher crack width, and an FR1K, which is a lower crack width. The next topic to talk about, and I do have to rattle through these fairly quickly, and there's a lot of technical content to get through as well, so apologies if I do touch on these subjects fairly briefly. Strengthening concrete structures with FRP is covered in this standard as well. It's proposed to be an informative annex, and it's likely to be adopted by BSI as an informative annex as well. There is some discussion in the UK group around some improvements that could be made, but obviously that'd only be made in a national annex with B525 agreement. The work is fairly modest in terms of its technical content compared to documents such as TR55 from 2013 or more recently the FIB guidance, FIB 90 from 2019. And that was really governed by the limited or page allowance really that was provided in the standard to the topic. So the provisions themselves are pretty succinct and cover only key areas, and there are areas where there is quite a lot of technical content which is enabling, but there are areas certainly where certainly in national annexes there might be some interest in developing the content a little bit. One of the key problems actually with codifying carbon fiber reinforced polymer, which is with the limitation in the annex, is that there are actually no harmonized European standards for the product itself or for how it's implemented, execution standards on site. There is a lot of work ongoing at the moment around what are called European assessment documents, which effectively become ETAGs or ETAs, technical specifications. But they are going through the system at the moment, and there have been no European technical assessment documents produced to enable us to work on those or to implement with those. And how we use ETAs or EADs in the UK post Brexit is probably yet unclear. EN 206 also needs to align for execution. There are execution provisions available for EN 206, but as it stands at the moment, that's sat with, again, the Technical Committee 104 to implement. The provisions themselves needed to enable, and again, they were carbon, where the provisions have been limited to carbon fibre in the standard, have needed to allow for products with very wide-ranging properties. So, for example, short-term strengths that can vary for carbon fibres between 1300 MPa and 2400 MPa. So quite a wide range and very linked to supplier capabilities. So very difficult to, whilst we did embark on trying to do it, to sort of codify into specific strength ranges or modulus ranges what we might get. So the provisions have been written around what's available on the market to enable producers to carry on what they're doing. But obviously the product and execution standards that come out obviously need to, put specific restrictions on the producers to make sure they align with the provisions that are there. There are specific provisions pretty typical to what you would, those who are familiar with TR55 or even may have had a look at FIB90 as it's been produced recently. But confinement effect in columns, shear strengthening provisions, basic SLS provisions to support deflection, deflection calculation, sorry. Two areas though where there have been specific additions are fatigue provisions. So it is possible with the code or the provisions that have been used to determine a fatigue life or a fatigue strength, I guess, of a system that's being used. And there is quite a detailed set of provisions covering debonding and looking at each of the individual failure mechanisms that can occur. Similar in a way, I guess, to what TR55 does do, but they are based on a different approach, which is published in the FIB90 guidance. And the provisions in this standard itself do look to align very closely to that FIB guidance. And obviously, as you'd expect, detailing provisions to enable designers to actually pick up and use them practically. I'm probably just going to skip over the next slide because I'm just running a little bit short of time. But if there's any questions on bond and anchorage, we can happily come back to that later because I've got some pre-prepared material. The next topic covered by the project team in the annexes was FRP reinforcement for concrete structures. Again, it's a newer area, and well, the latest guidance available. It's a newer area with old guidance, I guess. The latest guidance was FIB40 back from, I think it was 2003 or 2006. I don't recall the date. But again, provisions included that are proposed to be an informative annex. It's likely that the UK will implement them as an informative annex. But again, a set of provisions that deal with the wide-ranging properties of fibre-reinforced products. And in the case of reinforcement, there's no real limitation on the material, so it's open to glass fibres, carbon fibres, and even basalt fibres if they're there. Again, the provisions needed to look very closely at the wide variability, needed to as well allow for the future development of product and execution standards, because it is an area that's getting more attention, I guess, from suppliers now, and people are taking interest in producing these European assessment documents to be able to do it and get some commercial advantage. And again, it's an area that hasn't been previously codified in the UK or Europe. Obviously, there's been some ACI guidance that has been available for it. What did we do in terms of provisions? Obviously, FRP reinforcement, first of all, is not going to corrode, so it has markedly improved durability performance, which is obviously taken into account. It can be used. It does have a high strength, but it does have a very low modulus. So there is concern around again ductility, and so specific provisions have been put in to limit the use of the redistribution and plastic analysis methods in the standard that have been proposed, simply because they're incompatible. There is, of course, the possibility of using nonlinear FEA, but again, the failure of FRP material as a material is non-ductile. It doesn't have a post-yield behavior like reinforcement does. So it's a completely different consideration when you're looking at redistribution. So standard provisions: bending, shear, torsion, covered, etc. I did want to focus on one area of specific interest for FRP reinforcement around detailing, bond determination of anchorage length. I've just put an image in here of some of the systems available on site, and you'll see some products achieve anchorage by effectively gluing sand to the outside of the bar and roughening the surface, and other systems have a roughened profile to achieve bond and anchorage. And so the provisions in the code need to cater for these wide ranging scenarios that are there. And so that's been done. Again, producers will no doubt say that they have better performance than what the provisions allow, but the provisions of codifying something needs to inherently include provisions or an equation to calculate bond length. And apologies, I didn't put it in here. And obviously, there will be ongoing work in the European assessment documents that are produced to potentially enable there being improvements on that. And the provisions are written in such a way not to preclude that kind of development, because that is the sort of, going back to Tony's point around there being a code for use in 2040, these are the areas where we do expect there to be some development. And so we've had to write provisions in a certain way not to preclude that. So just getting on to the last couple of topics. I think I'm at time, so I know I need to saunter through a little bit. The next topic we covered was not a material related topic, but it was around assessment of existing concrete structures, which from the point of view of a project team trying to determine a remit of what they were meant to do with it was a rather interesting journey. There was not a particularly clear remit set by SEN on this, just to say add some provisions in, please, for assessments of existing structures. And the obvious starting point of that is we'll use the provisions in the standard, and they either do or don't comply. We did, however, settle on some provisions that were hopefully helpful. I know they've been contentious, and there's been a lot of discussion, and indeed there are an awful lot of comments around provisions on this annex, which again is an informative annex and is likely to be implemented in the UK as an informative annex. But an illustration of what we did, summary of what we did, there's already the possibility of using EN 13791 to calculate FCK, but that is clarified to make sure it's really clear how to determine FCK from the characteristic strength for design from cores obtained from site. So that's a lot clearer, I think, than what it has been in the past, and hopefully helpful. To assist, there's also an implementation of what's already in EN 1990, but it brings it out and makes a specific process for being able to determine the strength of reinforcement using samples obtained from site. more favourable determination of strength reduction factors, as Tony's already referred to, from sustained loading, so ECC. There is guidance in there around how to deal with, what to consider in relation to deterioration mechanisms, but obviously it's an annex in a code, so there's simply not enough space to give specific pointers as to what, or specific requirements as to what to do. So there is specifically guidance that says look out for these things and possibly other things. There is a bit more guidance around dealing with corrosion penetration, or chloride penetration, I should say, when dealing with capacity calculations. A couple of areas that, one area specifically where there were provisions, the full critical shear crack theory that Tony alluded to, explained earlier, has been effectively put into the annex and covers both shear and punching shear, again, as Tony alluded to, which is expected to be favourable in terms of existing structures. There was an interesting clause that's been put in, which has been accepted, around what to do with when detailing provisions are not adhered to in existing structures. And so there's a workaround where those provisions don't apply. So that's an interesting discussion with which leads you to the thought of, well, when does a building become an existing structure or not, and when can you actually use those provisions favourably, which is probably a topic for years to come. And very hopefully there was a piece of work done and actively participated in by a UK participant, John Cairns, with work led by a member of my project team, Fabrizio Parmesano, around calculating anchorage length for plain round bars. And I've put in the basic formulation there, but there is a lot of other paths to determining them. But hopefully pretty useful, because something we haven't had available before, in a way that can align with the provisions that we have in the standard now. And very finally, provisions have been included for stainless steel as well. And the simple aim of the work was to implement the use of stainless steel reinforcement into the new code and realise the benefit of its use. The provisions for stainless steel have ended up in 2 annexes in the new standard, both of which are normative actually, so are there and ready, I suppose, which is good. And they do very simple things. They introduce strength classes to align with EN 10370, which is subtly different to the carbon steel ones. Fatigue testing requirements to ensure adherence to the rules that are used in the main standard are introduced, and these were adapted from, or taken directly actually, from BS 6744 as pretty much the best guidance available in Europe. Ductility provisions and specific provisions around mandrel diameter, etc., are included, again aligning to 10370. And the work that Tony outlined around the durability section, there is a acknowledgement in there in the calculations of the improved durability performance in terms of determining the cover that you would use for a stainless steel bar. So I think in terms of the additional annexes, that's all I had to say. So I think with that, I'll hand back to you.
We'll now take some questions. Thank you for those who've submitted questions. I'll just take that off the screen, and hopefully you'll get back to seeing our speakers. Doesn't seem to want to disappear. Not to worry. So we've had a couple of questions. I don't know whether, Tony, you've had a time for a quick look. There's one from Arnab just asking about self-compacting concrete. Maybe a quick one for you.
Yeah. I mean, that's a very quick one. Self-compacting concrete, provided that's supplied in accordance with EN 206 BS 8500, is covered by the code. There are no particular rules. Obviously, if your self-compacting concrete is using smaller aggregates, then there will be a penalty in terms of depth factors, particularly for shear and the like, because all depth factors now generally relate to the aggregate size over the depth. So that's one thing to bear in mind. Yeah, so it shouldn't be a problem, but there may be consequences from the aggregates you choose to use.
Okay, thanks for that. And then
Could I add to that one?
Yeah, please do, Craig.
Andy? Yeah, there are actually, as well, to add to that, there are specific provisions that are included for steel fibre reinforced concrete around self-compacting concrete, dealing actually specifically with the fact that you may get favourable alignment of fibres, helping the tensile strength if you can prove that through testing as well.
We might just take a semi-related query from Alini. An interesting question, really. Is there any impact on the pressures onto formwork when fibres are added? I guess not. But Craig? What's the situation? This is the wet pressure effectively of concrete with fibres added. Is there any difference in performance in terms of the formwork design?
Well, it's certainly not covered in the code. It's certainly not a topic that's been raised. The density itself, there's no change in the density, which is the primary effect really on the design of formwork. So there's nothing significant enough to call for us to have put that in the standard. So I would say pretty much directly, no, not really.
Okay, thank you. We've got a question from Robert, which is interesting. Firstly, is the draft available? Tony, could you help me with that? Obviously, it was made publicly available at the end of last year, wasn't it? I know the Concrete Centre sent a link round, didn't they?
Yeah, so for a period of time, it was on the BSI public consultation web portal, so you could review it through there. But once the commenting period ended, they would have taken that down, and it's no longer available to the public. No, and as you know, as hopefully you got the gist from my presentations, particularly with regard to punching, there are still discussions going on. So I would say that the 2010 model code is probably the generally accepted best practice at the moment until we actually get a finalized Eurocode.
Yeah, so just to restate, it can be dangerous to look at these things and take guidance from them because the guidance can change, can't it, Tony?
Yeah.
For the time to come. Sorry, Alini, there was a question about pile cap design and strut and tie method, and whether there's an effect on minimum shear links. Tony, do you want to?
I'm not sure that anything has really changed in there. I mean, I think this is definitely one that comes a little bit down to engineering judgment, because if you're working it as a strut and tie system with direct struts, then you're not following beam theory. So what minimum steel do you need? There are requirements for minimum surface reinforcement where you're using deep beam rules. So you might consider that was a requirement, but I don't think that if you've got a proper strut and tie system and short enough spans, that you would necessarily provide minimum beam links for it. But I'm not sure that's a change in the new code to the old code.
Okay, there is another question from Joseph about punch and shear calculations and just questioning the approach, and particularly with related to time-dependent effects and load reversal and things.
Well, so Craig may be able to add to this, but I'll kick it off. Basically, the failure criterion is based on the strain in the reinforcement, and that governs effectively the assumptions on the crack width. Now, in the design part, so that you can get a closed form equation, the assumption is that the reinforcement is at its yield stress. In the assessment part, Craig might want to say something more. I'm not sure. You can consider the stress in the reinforcement directly, and if it's less than yield, get a benefit, can't you?
Yeah, in the assessment part, you've effectively got the full critical shear crack theory, so you're enabled to do the more detailed analysis and take account of actual strains rather than assuming that you go straight to yield strain. So as you pointed out, it's relatively similar to the modified compression field theory in the Canadian code, which is a similar thing where they, you have a simple implementation taking account, assuming yield stress, and that more detailed one taking account of the actual strain state. So that's what's been enabled in the assessment annex. Yeah.
So getting into the details of the points, I mean, as it's based on a failure criteria, then changing loads that doesn't matter because it's just considering the worst case strain in the reinforcement. Reversible loads shouldn't matter. I mean, there have been some discussions about reversible loads, but it's not explicitly considered. But obviously there are fatigue rules in the code. So if you have got a fatigue situation, then you would need to be considering your material properties for the fatigue case that you were examining.
Presumably that with a reversible load, there could in theory be some sort of a ratcheting type effect, could there?
Yeah, that's yeah. I mean, so another area which is akin to this is short shear spans. So there's an argument about when you have a moving short shear span, you might have a shear crack open when the wheel load, shall we call it, is in one place. Then you can't assume, can you not assume the same enhancement if that crack wasn't there when you get the short shear span effect. So there's some stuff around reversible loads and pre-existing cracking, but there's nothing explicitly dealt with in the code for that.
Okay, thank you for that. We'll just take the question from Costas, and this relates to assessment, and just a question that Craig might want to pick up. Did you consult with respect to seismic design when thinking about the assessment of existing structures, or is that being dealt with in Eurocode 8 specifically?
It's actually a really good question, and to be honest, it actually came up more on the FRP strengthening than it did in the assessment standard. Interestingly, the short answer to that is no. There is clear delineation in the SEN system between Eurocode EC8 and what we have in EC2. So that's all picked up there. We have obviously tried to align provisions as best as we can. We're trying to do that at a time when things are developing in parallel. And in fact, I think as Tony pointed out, the development of EC2 was slightly ahead really because of when the project teams were initiated. So I can't necessarily guarantee how the alignment is going to land once EC8's done, but we've certainly done what we can to use what's there in the current one, obviously taking account of what's been developed since the current EC8 was put into place. So I hope that answers the question.
Yeah, thank you. There's a question from Christopher that Tony might want to pick up on, and it's quite an interesting one. Are current punch and shear checks in Eurocode safe stroke conservative compared to the proposed standard? You might want to explain about calibration and what the teams do.
Yeah, okay. So at the moment, for the calibration exercises we've done, the new Eurocode would be more conservative than the current one. However, there will be further work needed either at the European level or at the UK level when we adjust or not adjust any of the nationally determined parameters. I think the general opinion is that the current Eurocode is far more conservative than BS 8110 for punch and shear, and we have no history of problems with BS 8110. So we're slightly wary of every time we we develop a method, we get slightly more conservative. So the thing to do is to understand why it's getting more conservative and how applicable that is to various situations. So the current punch and shear checks in the Eurocode are currently less conservative than that proposed in the standard. But I don't necessarily believe that the ones currently proposed in the standards will be the ones we implement in the UK with the UK National Annex. Indeed, one of the areas of work I was discussing with colleagues from Switzerland today, they're going back based on the work we've done to review the model over the next couple of weeks to see why it is that for the cases we've shown, it seems to be quite a lot more conservative. Because obviously, I mean, that has knock-on effects when you go to Craig's part and start doing assessment, because if the new rules all show that the old rules don't work, then it's quite hard to do an successful assessment.
Okay, thanks for that. And we'll probably just finish with a final question, if that's okay. More general question, really. You both answer this. How closely has the EC2 project team worked with the other Eurocode teams, i.e. other standards? Because there are areas of overlap sometimes. So could you just explain that and how things can get out of sync or in sync?
So firstly, there's horizontal groups that sit across various things. There's a horizontal group bridges, there's a horizontal group fire. There's an ad hoc group on robustness, for example, and they sit and look across the developing codes and try and get consistency across them. Then we have the actual other material Eurocodes, and sometimes there's less in the way of formal liaison across the groups. But obviously in the UK, I know the UK head of delegation for SC4, which is steel and concrete composite. So whenever I get something on particularly lightweight concrete or whatever, I often send that off to him and say, do you have any views on this? Because quite clearly, anything we do on the concrete side affects what they do on the steel and concrete composite side. But that's more of a UK thing than perhaps a European thing. Craig, any more?
Yeah, we had a lot of interest actually from the steel construction industry in the UK, funnily enough, on stainless steel. So we actually had some pretty good, really positive dialogue in terms of alignment of provisions that were being put into place regarding stainless steel in the EC3 and what we were trying to do with stainless steel reinforcement. So that was probably a bit more ad hoc, I think, not as an ad hoc group, but it was a bit more of a sort of an interest by others. But I suppose it does show that there was interest and people did know what was going on and were collaborating outside of the system as well.
Yeah, I think just to summarise on that, I mean, there is a question for BSI in terms of when the codes are introduced, and there's a lot of thinking going into which codes will be ready at which time, because I think the point's being made that we do need to think across all materials, and there is an interaction at lots of interfaces. I think we'll draw to a close at that time, and just to remind everybody that. Hope you've enjoyed this event. Thank you to both of our speakers. Thank you, Tony. Thank you, Craig. Thanks to the iStruct for hosting us. The next FIB event is on the 30th of June. It's another evening lecture like this, and we'll have speakers on prefabrication and durability, and we'll be announcing and have a presentation from our winner of our Coolest Concrete Award, which is a poster competition, who will present on their winning poster. So thank you, everybody, and we'll call the event to a close.